episode of Total Organic Chemistry. This time we'll be doing an introduction to aromaticity and how we determine that. By the end of this video, the questions that you should be able to answer are: what is aromaticity? How are the reactivities of aromatic compounds special? What makes a compound aromatic? And what are the properties of non-aromatic and anti-aromatic compounds? If you'd like some extra review on conjugated pi systems, which will be pretty important in this video, please go ahead and subscribe and click on the link at the top of this video. We can start with this hypothetical reaction where our starting material is benzene. This is this six-membered ring with these three double bonds here. And if we treat this with bromine, if you think back to your reactions of alkenes, you might expect this to maybe attack one of the alkenes and form maybe this kind of product, where we have the six-membered ring intact, and one of these double bonds has now been brominated, so we have these two bromines added anti across that bond. However, this reaction does not occur, and this should be our first hint as to why benzene and other similar compounds are very special. They do not undergo these addition reactions to the pi bonds in their structure. Another way we can examine how special these compounds are is through their heats of hydrogenation. And so if you remember from some of my previous videos, we can draw a reaction where we can take, for example, cyclohexene and treat it with hydrogen gas over maybe a palladium on carbon catalyst. And if you remember from previous videos again, these conditions are going to hydrogenate that alkene, turning it into the corresponding alkane, so this is just cyclohexane. And by measuring the amount of heat released from this reaction, we can get a sense for how stable the original compound is. And what that means is the more exothermic the reaction is, the less stable our original starting material was. So if we do this reaction, we might measure a heat of hydrogenation of about minus 120 kilojoules per mole, so reasonably exothermic. We can take this one step further and perform the same reaction with 1,3-cyclohexadiene. So in this case now we have two double bonds, but they are conjugated. Again, treating with hydrogen gas and palladium on carbon, we get the same product, just cyclohexane. And we see that the heat of reaction here is about minus 230 kilojoules per mole. And you might ask, well, why is it not double the first one? So why is it not minus 240? Because we have two double bonds. Well, remember, we noted that this compound is conjugated. So because of those conjugated double bonds, we get a little bit of extra stability in this compound. So we don't have quite as high of a heat of reaction. Finally, we might do the same thing with this hypothetical compound. We might call this Cyclohexatriene, and I'm going to purposely draw the double bonds very short and the single bonds much longer. So if we subjected this starting material to the same conditions in order to get cyclohexane as a product, if we just accounted for the number of double bonds and the conjugation in between each pair of double bonds individually, we might expect a heat of reaction of maybe minus 330 kilojoules per mole. So remember, we're saying that this is hypothetically the heat of reaction from hydrogenating all three of those double bonds, but we're also subtracting a little bit of energy because we're saying that these double bonds are conjugated in some way. However, if we perform this same reaction with benzene, we still draw benzene with these three double bonds and three single bonds, but when we measure the heat of hydrogenation, we find that it is actually around minus 206 kilojoules per mole. Not only is this much lower than the hypothetical 330 kilojoules per mole, it's actually a lower heat of reaction than even the cyclohexadiene starting material. So this might be surprising. We're adding an extra double bond, but we're actually getting an even more stable molecule. So why does this happen? Well, if we draw some of the molecular orbitals in benzene, we might find this diagram. So let's draw the carbon backbone, where we have this six-membered ring. And then we have these three double bonds. So each of these carbon atoms is sp2 hybridized, which means that each of them has an empty p orbital that we can draw. So we can draw these p orbitals coming out of the plane, perpendicular to the plane of the ring. And if you remember from our lessons on conjugation, these adjacent p orbitals can share electrons between themselves. But benzene is now special because we can have all 6 of these p orbitals sharing the same set of 6 electrons. So what we get in the end is this 6-membered ring of carbon atoms, but instead of having 3 localized double bonds that we can actually measure or distinguish from the single bonds, we can actually draw these double bonds as just a circle inside of the ring, because all 6 of those pi electrons are shared between all 6 of the carbons. So this is the start of our study of aromaticity, which is some of these cyclic, conjugated pi systems are considered aromatic compounds, and they are extra stable and have some interesting properties compared to their non-aromatic counterparts. Okay, so you might have noticed that I said some of these systems, so how do we determine what is aromatic and what is not? So this is where Hückel's rules come in, and these are a set of criteria that allows us to go down the list and determine if a molecule is aromatic, non-aromatic, or anti-aromatic. We'll talk about what each of those things mean in a second. So the first criterion is that our molecule must be cyclic. This is pretty straightforward. What that means is if we have a molecule like hexatriene, which is indeed not cyclic, this is not an aromatic compound. On the other hand, if we look at benzene again, this is indeed a cyclic molecule. We have this 6-membered ring, and therefore it has the potential to be aromatic. Next, this molecule must be conjugated all the way throughout the ring. So again, we can look at cyclohexatriene, where we have these 2 double bonds now. And although these 2 double bonds are conjugated, we still have these 2 sp3 hybridized carbons on the other side of the ring, so it's not conjugated all the way throughout, and therefore this molecule is non-aromatic. Again, looking at our model, benzene, these 3 double bonds mean that we have sp2 hybridization and therefore conjugation all the way throughout the 6-membered ring. The next rule is that the molecule must be planar, so this whole ring has to lie in one plane. It can't bend out of that plane at all. A popular counterexample for this is Cyclooctatetraene. So we have this 8-membered ring and 4 double bonds that are all conjugated. So again, this molecule is cyclic, it is conjugated all throughout the ring, but we need to think a little bit about the geometry of these bonds in order to determine if it's planar or not. And it turns out that with this particular compound, if we kind of draw it from the side view, it adopts this sort of geometry, where these 4 carbons are in the same plane in the middle, but we have this boat-like configuration where the double bonds at the ends are bent up and out of that plane. So because this molecule is not planar, that really nice conjugation that we had with benzene, with all of those p orbitals perpendicular and adjacent to each other, doesn't really occur. The last rule is that we need to have a number of pi electrons that equals 4n plus 2. Another way to think about this is we need an even number that is not a multiple of 4. So we can have 2 pi electrons, 6, 10, 14, etc. So again, if we look at benzene, we have 6 pi electrons. So these 3 double bonds again contribute 2 pi electrons each. So we have a total of 6, which is a Hückel number, and therefore benzene is aromatic. On the contrary, if we draw Cyclobutadiene, so this 4-membered ring, we can see that it is cyclic, it is conjugated throughout the ring, it is planar, so because we have this 4-membered ring, none of the bonds are really able to bend out of that ring. But finally, since we have 2 double bonds, we have a total of 4 pi electrons, which is not a Hückel number, and therefore this molecule, because it satisfies the previous 3 rules, is called antiaromatic. And antiaromatic compounds are a very special class of compounds that have a special instability, whereas aromatic compounds are especially stable. So using these 4 rules, we can determine if any compound is non-aromatic, which is the majority of organic compounds, aromatic, like benzene, or antiaromatic, like cyclobutadiene. To end this video, let's see some examples of compounds that we might not notice are aromatic right away, but nevertheless are aromatic if we look at them a little more closely. So if we draw this 5-membered ring with 2 double bonds, this is cyclopentadiene, we can go down the list of Hückel's rules and determine whether it's aromatic or not. So first, it has to be cyclic, and that is true. However, the next rule is that it's conjugated, and although we have these two conjugated double bonds, we do have this one carbon that is sp3 hybridized, and therefore the ring is not conjugated throughout, so this molecule is non-aromatic. However, if we treat this compound with a strong base, we do have these hydrogens on that sp3 hybridized carbon, and those hydrogens are pretty acidic because of the double bonds on this ring. So what that means is we can end up with this anion, so the conjugate base of cyclobutadiene, where now we still have these two double bonds, but now we have a lone pair on that carbon, and with that lone pair again a negative charge. And if you remember from my video on carbocations, carbanions, and carbon radicals, you might know that this carbanion is going to be much closer to sp2 hybridized than sp3. What this means is that this lone pair occupies a p orbital that is perpendicular to the plane, instead of maybe an sp3 hybridized orbital. So now we can see that in addition to being cyclic, this compound is now conjugated, because this lone pair of electrons is delocalized throughout all 5 of these carbons. We can draw a resonance structure, for example, with this lone pair coming down to form a double bond between these two carbons. Now we have this double bond swinging over one, to where the electrons in this double bond are now just hanging out on this carbon here. And you can repeat that for all 5 carbons in the ring. So again, that means this structure is conjugated, and it's also going to be planar. We have a pretty small ring, and these double bonds are going to really force that into the planar configuration. And finally, if we count the number of pi electrons we have 2 from each of the double bonds, and again we have these 2 additional electrons in the lone pair, and we count those in the pi electrons because, like I mentioned, they are occupying a p orbital, so they are delocalized into that pi system. So if you add those up, that means we have 6 pi electrons, which is one of our Hückel numbers, again, even numbers that are not multiples of 4. So this anion is actually aromatic. So this is interesting because not only can we have aromatic compounds that are neutral, we can also have anions or cations that are aromatic as well. Okay, let's look at one more compound. So this is this 3-membered ring where we have this double bond on these 2 carbons here, and then let's have this ketone coming out here where we have this double bond to oxygen. So if you go down the list of Hückel's rules again, we might see that we have a cyclic compound. However, it's not really apparent that this is conjugated. So we do have this double bond here, so we know that these 2 carbons are good. But what about the carbon with the double bond to oxygen? So we're not so sure about that. Well, we can draw a resonance structure for this compound, where we swing up one of the pairs in the carbon-oxygen double bond up to the oxygen. So this gives us a negative formal charge on the oxygen and a positive charge on the carbon, so we now formed a carbocation. Hopefully this is a little more apparent that we have a conjugated system, because we can draw another resonance structure with this double bond being delocalized throughout the whole ring. So swinging this double bond over will give us this resonance structure with the positive charge on this carbon on the left and the double bond between these 2 carbons on the right. And again, you can repeat that once more to get the positive charge on the bottom right carbon in the ring. So finally, what that means is that we have a cyclic, now conjugated, also planar, because any 3 points form a plane. And again, if we count the number of electrons, we can see that there are 2 pi electrons in the ring. Only the 1 double bond here, because the carbocation has no additional pi electrons to lend us. And remember, 2 is one of those good numbers again, so this is indeed an aromatic compound. So those are some important considerations when you're determining if a compound is aromatic, non-aromatic, or anti-aromatic. I hope this video allowed you to do that a little more effectively and efficiently. If you haven't already, please give a like and subscribe to the channel for more. Follow me on social media, and take a look at my website on the screen. And finally, if you're willing and able, consider donating to my Patreon page, which helps me to continue creating all this content for all of you. Thanks for watching.